Good morning, everyone. Thank you for coming today. I have a quote for you all this morning. It is my personal quote, and I think this is a quote that is it'll see us through. It will see us through. So let's put the quote at the top. It's kind of bad if you forget the quote, right? No, whatever. It's a quote that's out there, but I just took it and just made a few changes. Let me rephrase, right? There's this quote I found online, and I made it personal. Right. Doing what others want so that I can have what others don't. You all find that's a beautiful quote? Exactly. How is this applicable? Because you all are here in study group over the vacation, studying when no one else will or wants to, so that you all can have an A. So you all can have an A, right? So that's good. What's the one? I'm listening, talk to me. Yeah, so session number 3, this is our goal for today. So this is today. We want to go cosets. Well, session 4, more or less session 3/4. Oh my God, I'm in Lagrange. Theorem, homomorphism, isomorphism. Nice. So hopefully we'll be able to get through all of this. I don't see a reason why not. I have gone through the material and I have done the term analysis, so we should be fine. And it will be, as usual, a relaxed, intense feel. I love that phrase, you know. So does everyone have the updated version of the notes? Yeah? Good. Email was sent last night, so thank you very much. You'll thank Chris and Aliyah for organizing that. Well done. So we are on definition. In fact, before we get to that definition, while I was viewing Mr. Ramnanan's section, he had S3. You all know what S3 is, yes? Yes, sir. The symmetric group on 3 elements. Oh my God, that is so brilliant. Yes? You all remember? Good. And he had A3. You all remember the elements of S3? S3 is a group, yes? Good. So we have 3 elements, yes? And we're going to permute the 3 elements. So if we do not permute the elements, what permutation is that called? The identity. Well, that is beautiful. So we have 3 elements. We need to change 2. Which 2 we could change? Or we could keep 1 fixed. Let's keep 1 fixed. Which one we want to keep fixed? What number? We could keep 1 fixed. Assume 1, 2, 3 are our elements. We keep 1 fixed. So then which are the other two elements that are left? 2 and 3. So we can permute 2 and 3, yes? So we permute 2 and 3. This is keeping 1 fixed. If we keep 2 fixed, then what are the other 2 elements to permute? 1 and 3. If we keep 3 fixed, the other 2 elements are 1 and? Lovely. So we have these. Now if we permute all 3, right? So we have 1, 2, 3, and then we can have 1, 3, 2. Everybody's okay? Nice. A3 would be the alternating group, and this would have E, and this would have these 2 elements because they have 3 elements in it, right? I don't want to go too much into the details of that. Again, that was covered by Mr. Ramana. Arising from this, he mentioned that to show that this is a group, you all could do the multiplication table, yes? So just to make it clear, just to make sure you all understand exactly what he's speaking about, we would have E 1, 2, 3, 1, 3, 2, 1, 2, 3, 1, 3, 2. And you would literally permute these, right? So E by E is E, so this is just going to repeat. This by this, so this is going to repeat here. And these things here you'll have to work on, right? You'll know how to work them out, yes? So this one here, so this would be 1, 2, 3 by 1, 2, 3, which would be? Anybody? So we start with 1, yes? So we start with 1. 1 goes to 2. 2 goes to. So then we start with 3. 3 goes to 1. 1 goes to. No, sorry. We start with 2. 2 goes to. 3 goes to. 1. 1 is repeated, right? We close. Yes? You're good? So this goes 1, 3, 2. And then this by this. So 1, 3, 2 by 1, 2, 3. Anybody could guess what will it be? Random guess. E. Well done. So that is the next point. Each row must have all the elements if it's a group, right? But in how we pose the question was to determine if, which means you would have to multiply them and show that it's closed. Arising from it, we just want to remember the theorem H dot H equals to H. This happens, if this happens and it's a finite group, it's a finite set, then it's closed, right? That was the theorem. Mr. Ramana mentioned that you need to check for identity, but he wasn't too familiar with this theorem, so I just showed him, and he said, okay, go. So I just want to clear that up. So let's just work this out. So we start with 1. 1 goes to 2, and then 2 goes to, so it goes where it closes, yes? We start with 2. 2 goes to, 3 goes to, 2. Closes. We start with 3. 3 goes to, and 1 goes to, 3. It closes, yes? So that's how we get E here. Everybody's okay? And you all will be able to fill these out, yes? Not going into that. But everybody's good, yes? Nice. In fact, take a minute and filter. Yeah, take a minute. Do it. It's just revision. Do it and we'll just all check, make sure everybody has the correct answer. And we'll move on so it's complete. This one is? Anybody? E? Yes? And this one is? Aha! What will that be? 1, 2, 3, yes? This is 1, 3, 2 here, right? This is 1, 2, 3. Everybody's okay? Anybody can notice anything from this table? Look at it. Ah, boy. So just ignore that. So that's our mirror line. Seam. Oh, wrong one. That's any tape. So seam. Jump. Seam. You'll follow, right? Yeah. If it were a random operation we did not know, then you would say it's commutative, right? Because A star B would be B star A, right? Nice. Perfect. It's definition 3.1. So we are on Cosets. Everybody's with me? Nice. Definition 3.1. Let G be a grouper with subgroup H dot. For all G in G, we say that A is congruent to B mod H. Oh my God. And write A 3 lines, open brackets, A 3 lines B mod H. If and only if A be inverse element of H. That's a definition. That's definition. Can't really do anything. It's a definition. You all follow? So let's just understand the definition very briefly. It's not much to understand. So if I were to have M P mod H, what does this mean? Loosely, we want M by P inverse element of HS, is mod HS, where M and P are, where are M and P? Are M and P in H or are they in G? They're in G, yes? So M and P are in G. So it's the group, not the subgroup. Everybody's okay? Nice. Now again, this is abstract algebra, so it's starting to get a bit abstract, right? Don't worry, by Wednesday, so I'll bring it back, and the repetition that I will constantly be doing throughout these lectures, it will be very familiar to you. By Friday, when we go through what we've done and what we've covered, and you can look at something and read it and go, oh my God, I understand. You will feel amazing. Trust me, you will feel amazing. I cannot wait on a personal note to reach the Isomorphism Theorem. The Isomorphism Theorem is amazing. It is brilliant. Prior to, I can read this, right? Yeah. So prior to coming into U.W.I, I never really understood why maths used to give people problems. You know, it's maths, I mean, it's nice, right? I mean, I do well in maths, it's logical. Lo and behold, I met this course. And then, in this class, this is where I realized, oh my God, there are some things in life that you just cannot understand, right? And then after you spend time with it and you keep on going, you trust me, you will feel, if you put in your work now, which I highly recommend that you put in your work, and I know you're all putting in your work because you're all watching the videos and coming to classes. There's no way you could come to class and listen to me and not learn anything. That's like impossible, right? Take a little part of my back there. Thank you very much. Yes? You will feel a different part of your brain working, right? You'll be like, I'm confused. That's normal. That is fine. It's a rite of passage. The good thing about it is that will happen now compared to during the semester when that has to happen and you have 4 other courses to do at the same time. You all understand? 5 other courses, 6, it doesn't matter. But the good thing is that it will happen now. Good, so we are on theorem 3.2. The equivalence, so the relation, 3 arrows, so the equivalence relation, the relation mod H is an equivalence relation. You'll remember what an equivalence relation is. An equivalence relation is a relation that is reflexive, symmetric, and transitive. And what is one of the most important things about an equivalence relation? Don't know if you all may have gotten this in year one. But one of the most important, beautifulest ever thing in the whole world is that the relation partitions the set. You follow? In other words, it will divide your big set into smaller sets that have the properties of a partition. You all remember what the properties of a partition are? Of course, yes. So a partition, you all want proper stuff or no? No, because it's simple. I mean, this is not necessary. This is.
It's sufficient.
A partition P of a set A is a set big of subsets big again that are one non-empty, two disjoint. Subsets and for the union of which gives, which means is, A. So in other words, let's just put this into maths a bit, right? Calm down. We have a set A. Let's just call this set 1, 2, 3, 4. Yes? If I were to say P, if I'm creating a partition, right? P, a partition P of a set A, so A is a set. So we have set brackets, yes? Is a set, I really don't know, is a set of subsets. Obviously it has to be subsets of A, right? So in other words, the elements are from here. So in other words, okay, I know I have a set, and in this set I have subsets. You've seen it, right? That are one non-empty, so which means these brackets must have elements, yes? Two disjoint, they cannot have any repeat elements. Somebody call an element here. One. Call an element here. Two, well done. Subsets, which means all the elements are from here, yes, that's fine. Such that the union gives A. So in other words, if I were to union this, I should get back A. So this as it is this a partition of A? Why not? Because it's missing 3 and 4, yes? Great, so what will I add here? 4. And I could add 3, yes? You all see that, right? And it will still work, yes? Oh, I could do that as well. And I'll still work, yes? Because each one is non-empty, there were no repetitions, and the union of all gives back my set, yes? Good. And what this partition does, it broke up this set into smaller sets. So we could work on this, and we could work on this individually. You all follow? Yeah. If I were, so this is a partition, P, yes, everybody's good. If I were to add 5, would this be a partition? No, right? Why? One more time. That's correct as well. But the better answer, I shouldn't say better answer because once you contradict, you still get marks, would be 5 is not an A. You all follow? Everybody's okay? Beautiful. So, how do we use this in mathematics? All of this is a bit tangent. I'm just making sure you understand properly. So let's say I have Z. Everybody's okay with Z, right? Dot, 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 minus 3, minus 2, minus 1, 0, 1, 2, 3. A partition of Z would be what? We could have odd. So odd would be n such that, in fact, let me don't go there as yet. Odd numbers. Minus 3, minus 1, 1, 3, dot, dot, dot. Yes? Everybody's okay? We would have even, which would be minus 2, 0, 2, dot, 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 right? 4, dot, dot, dot. Everybody's okay, yes? How I could write this differently? So this would be my n. So this would be my 2k plus 1, where k is in Z. So this gives me my n, right? This all my numbers here are odd. And if I wanted to write even, this would just be 2k, where k is in Z. Yes? So if there were a proof, and sometimes you would need to use this in induction when you are doing divisibility proofs. And let's just say you come with some expression and you have to show that that expression is divisible by 4 or 5. What you do is you say case 1 when n is even, and you replace n as 2k plus 1, 2k, and then you go down and then you solve. You say case 2 when n is odd, and you replace it by this, and then you go down and you solve. And since it works in both cases, then it holds for each set of integers. You all follow? That's the beauty. That is the beauty. So that is on a practical scale. So we are right now, we have cosets. We've now defined what a coset is. We've now defined mod H, and now we are going to define this. We are saying that mod H is an equivalence relation, and why that is important, because it partitions a set, and in this case our sets are groups. So we are partitioning the group into some weird thing that we will see eventually. You're understanding the storyline, right? Beautiful. Proof. So we need to show reflexive. You all remember reflexive, right? Reflexive says for all A in the set, so the set is generally A, we want to show that A is related to A, yes? That is reflexive. Then we have symmetric, which says that if, remember symmetric is a conditional. So if this happens, then something else happens. So if A is related to B, then we want to show that B is related to A. It doesn't say that we must have an A and a B related. It just says that if this happens, then that has to happen, yes? If you have somebody, if somebody comes home by you, then you need to feed them. It doesn't say that somebody is home by you. You're following? Yeah? So this is what? Symmetric. And the third one is transitive, which is if A is related to B and B is related to C, then A is related to C. Everybody's good? Yes? And this is transitive. These definitions are not in your notes. They are in your year 1 notes where they should be. So I can erase this, yes? Right, so let's get to the proof. So we would like to show reflexive. So we are in the notes, term 3.2. Proof for all A in G. So for all the elements in G, we want to show that A is in G, yes? But what does right, so just briefly, let's translate what each of these means. So in maths, and in particular in this question, this says that for all A in G, we want to show A is related to A, yes? But our relation is what? Mod H, yes? So we want to show A, 3A, which means what? A by A inverse is in H. You all follow? This one says that if A is related to B, now we know A mod H gives A, B inverse in H, yes? We want to get that B is related to A. B being related to A means the first, remember, A is the first element, B is the second, sorry, so it's A by B inverse, so the second element is the B inverse, right? So B being related to A means B by A inverse is an H. This is what we want to show, yes? You're following, yes? The last one says if this and this happens, then we want to show this. So in other words, if we have, so I'm just going to jump into it, A, B inverse, so if A, B inverse is in H, and B, C inverse is in H, B, C inverse, then we want to show A, C inverse is in H. Yes? A, C inverse is in H. Everybody's good? Nice. So we go with this plan. So proof. Take a minute. I'm waiting. Sorry, we're not leaving anyone behind. Right, so we take an element in A. So let A be in G. Sorry, our set is G. So we are in the notes, right? So you can look at the notes. This is literally in the notes. So for all A in G, A by A inverse is E. And we know that E is in H. Why is E in H? Because H is a subgroup, right? Since H is a subgroup, it means that H is a group, right? And if H is a group, H has to have an identity, usually called E. Everybody's okay? Which implies that the relation is reflexive. Everybody's good? Nice. Symmetric. So if A is related, if A is congruent to B mod H, then A, B inverse in H. So we have this here now. So we have A, B inverse in H. Now, since H is a subgroup, H is a group, and all elements in a group have inverses, yes? Which means then A, B inverse, all inverse is in H. Yes? And when we take the inverse of A, B inverse, so in other words, we have the inverse of A, B inverse is B inverse inverse A inverse, which is B A inverse, yes? And that is exactly what we have to show. B A inverse is an H, which means that the relation is symmetric. The last one, the last part, so we set it up again. If A is congruent to B mod H and B congruent to C mod H, then we have these two equations here. Yes? And so in other words now, so we have A, B inverse and B, C inverse in H, yes? Could anybody see how I can get A, C inverse in H from this? What do I have to do? Just multiply, right? You all see it? So I can multiply, I mean, anybody could say just multiply, right? Psh. But why? Okay, I can multiply, that's fine. But how will I know that this is in H? Okay, I multiply two elements, but why is it in H? The reason is Talk! Because H is a grouper, and a group is closed on a multiplication. So we know we have two elements in H, which namely AB inverse and BC inverse, and these are elements in H. H is a group, H is closed on a multiplication, so we can multiply them and we will still get an element in H. You follow? So we just multiply them. Y'all want to see the dot? And then this simplifies the AC inverse, and we know that AC inverse is in H because it's the same. You follow? Therefore, it's transitive. A congruent B mod H is, so the relation mod the congruence relation is transitive, yes? Nice. Anybody has any questions? This is beautiful. Because we have now proven that we've now proven that we have an equivalence relation, which means we can partition the group. Which set will this equivalence relation partition? G or H? G, because the elements are from G. You all follow what's going on, right? Lovely. Definition 3.3. The equivalence class containing A is HA, which is the set of all elements HA such that H is in H is referred to as the right coset of H in G. So the right coset of H in G. So we have HA would be the set of all H's by A such that H is in H. Yes? Note A is to the right of H. That's why it's called the right coset, yes? The left coset, when we say is analogously defined, is A is just to the left, right? Everybody's okay? Straightforward. So let's just go back. I love the complex example. I just find it so beautiful. Complex numbers is the best thing in the whole world for me. That is the main reason that and vector spaces are the two main reasons why I did a degree in maths and then my master's. I love vector spaces, which you all would be introduced to in second year, first semester, linear algebra. It is like the best thing in the whole world. Just love it. Anyhow, enough about me. So we have G. Let's just call this set G1 minus 1, I minus I. Yes. And we have a subgroup of, so this is a group along with multiplication, right? Everybody's okay, yes? We just call this G. It's fine, right? So instead of G comma dot, G is the group, yes? H would be, what is the subgroup of this? You all should know by now. 1 minus 1, yes? 1 minus 1. Lovely. Oh, so where does A come from? A comes from G. Yes? A comes from G definition, right? It really, I mean, it could come from H, but if it's in H, then it's in G. You follow? Because the next term says that if it is in H, then the left coset and the right coset is the same, which is equal to H. Yeah? So A is in G. So in other words, so this is my H. And this is a subgroup of G, and it is also a coset, yes? Lovely. If I were to take a next element from G and multiply it, so if I say H by 1, H by 1 gives, you would multiply this now, because multiplication is commutative, in this case it makes no difference, yes? Because 1 by 1 is 1, 1 by I is I, and I by 1 is I, right? Lovely. So remember, when we're dealing with groups, the multiplication, the operation could be anything, right? So we can have operations that are non-commutative because a group does not have to be commutative. A group has to be associative. If the operation is commutative, then it is called an abelian group, yes? Beautiful. So this gives 1 by 1 minus 1 by 1, which gives h, yes? If I were to multiply it by minus 1, so h by minus 1 gives 1 by minus 1 minus 1 by minus 1, which gives minus 1 by 1, which is still h. Remember, a set. You all know what a set is, right? Set is unordered, means that the order does not matter, right? And you could repeat elements, but do repeat elements, right? You're just wasting time. If I were to multiply h by I, you know what you get? Hi. Oh my god, this is brilliant. You see what happens? You make up jokes on the spot, you know. I'm just too good, boy. I'm too good. You get a 1 by I. You get a minus 1 by I, which gives, I'm tempted to say hi again, you know. This gives I and minus I. Yes? And if we were to multiply h by minus I, y'all know what I get? By. Like minus high is by. The inverse of high is. This is what happens, you know, when you get into the mode. It's just this mode that switches on and everything flows. Right, so what do we get? We get minus I by I, which is the same as this, yes? Which is the same. Lovely. So what we realize is we have two sets, one, and this is the other set. So this is called H, and this is called HI, yes? So the partition would be what? Y'all write down the partition. Somebody write down the partition of G induced by the cosets formed by H. We've done all the work there. It's just literally to write it down, to show your understanding, to make me feel good. Anybody is lost? You're good? So the partition would be first thing, our partition is a set. So we have a set of subsets, and we've now realized that we multiply all these elements and we really only have these two sets. So the first one is H, and the second one is Hi. HI. Yeah? So we can rewrite this as H. This is sufficient there, but I'm just over explaining so you all understand, right? Which is 1 minus 1 and I minus I. You all follow? And what does this partition G in? 2. This is what? Something numbers. And this is something numbers. Not a number of numbers. What kind of numbers are those? What is my name? What is the first letter of my name? Real numbers. And well done. Y'all see that? So the partition G into two sets, real numbers and complex numbers. So if we were to do some more analysis, we could do analysis on the real numbers and on the complex numbers. Y'all follow? Good. But if I were to ask you to partition this by it in some way, you see what happens is the equivalence relation partitions the set naturally without us having to ensure that it does it so. You all follow? Lovely. Good. Theorem 3.4. If A is in H, then AH equals to HA equals to H. So in other words, AH is what? That's like what? Ah equals to ha equals to H. I am sorry for you all. You all have me for 3 hours like this. Oh joy. So we have to show. What do we have to show? Somebody, what are we required to show? Anybody? Just read it. Just read it. Anytime AH equals to HA equals to H, yes? Yes? Let's just take one side, right? AH is a what? S. E. Set. HA is a set. How do you show equality of two sets? Subset, yes? You all understand, right? So in other words, my proof for this should be let, I'm just using random, right? The proof is there, it's in the book, but I'm giving you all these stencils so you'll understand what was done. So in other words, I have to take an element X in AH, do some working, and show that X is where? In HA, yes? Everybody's okay? And having taken an element here and show it is in HA, then that would imply that where I took the element from AH is a subset of HA. Call this equation 1. Yes? Then I have to do the converse. I have to take an element from here and show it is in here, which would mean that HA is a subset of AH. Therefore, using 1 and 2, we get equality sign. You follow? And then we take the other equality sign. Yeah? Well, these are really baby steps I'm going through, right? Also, so yeah, we can do it here. Conversely, who say math people don't know big words, huh? Conversely. Hey, calm down. Let X. Just have to go and burst the bubble, you know. Who say that's not a big word? Who say that's a big word? Y in, we took the element where we need to take it in HA now. Working, and then show that Y is in AH, and that would imply, I'll put it here, that HA, where you took the element from, is a subset of AH. Call that 2, 1, and 2 implies HA equals to HA. Everybody's okay? The proof is in the text. Let's just go through. So let H be an H. Then H. So H. Again, this is really baby. I mean, it's kind of insulting your intelligence, but you know. So the next line we have is HA inverse by A. And how did this come? We know that H, any element, is itself by the identity, yes? So this was H by E, and then we write E as A inverse by A, yes? And then because, why could we do this? Why could we switch these brackets from here to here? Because it's associative, yes? And it's a group. These are the things you have to make sure and mention, right? So just add a T in there. And these are the things which you lose marks for, right?
Oh, okay.
Yeah? Now it's not a matter of just writing A by H and H inverse. Now it's Y. Yes, if you can understand why, because that means you understand the structure of a group and you understand the algebra behind it, which is what we want. Nice. So from that we group this and we call this H1. So we have H1A. So it's of the form H by A, which means that it is in capital HA. Yes? So therefore, we've taken an element in H and shown that it is in HA. Everybody's okay? So instead of using HA and AH, we used H and HA. Yeah? Conversely, so now we take an element in HA and we need to show that that is in H. Since A is in H, then HA is in H. Therefore, HA is a subset of H. Everybody's okay with that? You understand why that is, right? Because H is a group, right? And H is closed. So if A is in H and if A is in H and H is in H, then AH is in H. Closure, right? Therefore, we have HA is a subset of H. Hence, we've got equal sign. And then you can do the same thing for H, for AH with H. You follow? So in a proof, depending on how formal you want to be, you could write this or you could actually do it out, yes? So this could be a nice little exercise. So exercise, fill in the blanks, right? So instead of writing the word similarly, do the proof, yes? Anybody has any questions? Lovely. Lemma 3.5. Let H be a subgroup of G. So in your head you're thinking, okay, you have a group, you have a subgroup. So you're thinking cosets one time, right? Group, subgroup. Then the left coset of H in G then the left coset of H in G has, that have supposed to be has, right? Has the following property. So just somebody highlight that, yeah? You have to be grammatically correct as well, you know? Cosets. Okay, so it's correct. Just testing you out, you know? Wow. Anyhow, property 1. If X is in XH, if X is in G, then X is in XH. So if you have an element in G, then it is also in the coset of that element with H. You all okay with this? Point 1. So if X is in G, so in other words, if we have G, so if we have G and we have an X in G, this is G and this is H, then XG, XH, X by some element, so H, call it H, will be in H. Do you follow? And we know that is true because H has the identity element, which means that X by E is still X. You follow? And this X was in G. So this means that is an XH since E is in H. You follow? This is more or less straightforward. I mean, these things are just go through. The second one, if X and Y are elements, ooh, this is a nice one. I want you all to try this one. The proof in the notes is different. Ha! So that's good. If X and Y are elements of G, and if yx equals to a for some a and h, then xh equals to yh. That is a beautiful proof, which we will all do together. But first, I will allow you all to try it. So we have H is a subgroup of G. Y'all were introduced to this notation, yes? Yeah? Nice. So H is a subgroup of G. We have X and Y in G, and Y equals to XA for A in H. And we want to show that XH equals to YH. Right. I will start you all off with the word proof. Take a few minutes and think about how you will do it, and then I will start. In the format, you'll understand the format of the proof. I'll give you all the last line. What is the last line? H XH equals to, it's brilliant. I'm that helpful, aren't I? XH is a set. YH is a set. Therefore, we have to have subset, subset. That's all. With that, you should be able to finish the proof. So let's go. Let's take an element in this, yes? So let XH1 be in XH. Yes? Good. Now our goal is somehow, somewhere to show that XH1, well, sorry. Alright, so there's just one line before that. It's not necessary, but I think it'll just make the proof. Okay, that was the advanced part, right? This is the basic part. Let Z be in XH, yes? Then Z equals to what? X by H1 for some H1 in HS. Everybody's okay? Yeah? Leave it. Our goal is to show what? That Z is in YH, yes? So somewhere down here, somewhere, I don't know where. Here, so our goal is to show that Z is in YH. Yes? Good. What do we know from the question? So we have to use something from the question, right? What can we use? H is a subgroup of G. Okay, good. We know H is a subgroup of G, yes? X and Y and G. Okay, alright, great. Oh my God, look at this. This is brilliant. You all seen it? Neither me, I didn't see anything yet, but I just know it has something there. We didn't use it yet, right? So how could we use this? We have XH here. Wait, why not make X the subject of the formula? You all follow? So this would imply that X equals to what? Y A inverse. And why could we do this? Because A is an H and H is a group, so inverses exist. Therefore, that's the only reason why we could get A inverse. You all follow? Nice. So now we could call this 4. I don't know why. I just decided to call it 4. Right? We could. Anybody guessing? Substitute 4 into 3. Yes? Well, y'all could do it, right? So what we do is A by H associative, yes? We could write that as H2, where H2 equals to A inverse H1, and that will be in H because H is a group and inverses exist and is closed, so A inverse H is an H, yes? I will keep repeating it just until you all have it. Forever and ever, right? Which means that we have shown that Z is Y. Look at here, Z is a Y by some H2, which is an H, therefore we've shown it, yes? Was that difficult? Not really. We just followed some steps, we understood what we needed to show, and we showed it. Therefore, we took the element in XH, which implies that XH is a subset of YH. Conversely, you all want to write down the converse part? Let W be an element of where? Where? YH. Take a minute. Shortcuts, we're doing it proper, taking our time, proper, complete, so when the time comes you know exactly what's going on. We can call this equation 1 because they gave it to us, right? So that's a little tricky to read. after, it's not really a trick, it's laziness. You know you're going to use an equation that comes somewhere in the middle of a proof, and you will use things that came before. Never label it 1 because there will be equations above, right? So this is equation 1. So substituting 1, you'll just, if you see I keep writing this small, just give me a little reminder, I need to write this font, right? For the camera, right? But then again, if you're watching a YouTube video, I'm speaking, so you'll know. Into 2. It's generally not the best way to do it. We have bad numbering, right? But still correct, right? We have 3, 4, 1, 2. That's fine. We get W. Oh, I forgot the line. Let W, then W equals to Y by H. 3. You'll allow me some cut and paste, right? So we cut this and we just put it here. We get equation 2. W equals to Y is X. A, we have H3. And remember, we want to show it is in XH. This here, associativity, we have X by H4, where H4 is AH3, which implies that W is in XH. Everybody's okay? Therefore, where we started, we took our element from YH. YH is a subset of where we ended up, XH. Call this A, call this B. From A and B, we get. Y'all see how nice that worked out? I'm just impressed that I wrote this here at the bottom and it fell right in place. Y'all good? Yeah, no longer too much concern about the understanding. Y'all get the understanding. It's just the art of the presentation now. It's artistic. Right. The third one, if X and Y, anybody has any questions? Everybody's good? You're with me? Simple enough, yes? Good. Y'all don't worry, it's like you're climbing a little hill. You won't feel it, but when you reach on top of the hill and you turn around, you're like, oh my word, look at the distance we've covered. Look how high we are. Sorry. What's that? No, you can't fall. This is because it's an abstract hill. Yeah, can't fall. Part 3. If X and Y are elements of G, and if X, H and XY is non-empty, then XH equals to XY. Now I have this little note here. Remember, cosets is an equivalence relation, which we did before, and equivalence classes. So HX and HY would be equivalence classes, yes? Which means that they are. Okay, so there's in year 1 there's a proof which says that equivalence classes are either disjoint or they're equal. So if there's a common element in one set, that means there must be the same. Yeah. So that's a standard proof there. It is in the notes, which is straightforward. So I'll leave that for you to go through. So we've completed one entire page. So now we will go to lemma 3.6, which I will not spend much time on. Let H be a finite subgroup of G. So in this mini abstract study group, the reason I call it mini because if you say you're going to abstract study group, then We want to cover a lot of stuff, but we are just covering the essential. This is the bare skin and bones. This is not even bones. This would be like the blood and the calcium that forms the bones, right? So I'll just read it. So proof, let H be a finite. My point was, in group theory, we want to pay special attention to finite groups and infinite groups. Yeah? Because if things are finite, then there will normally be a corresponding theorem for something that's finite if there's one for infinite, and the corresponding for finite. There's a little, what's the word, boy? There's a little more freedom in it. So for a subgroup, you remember, if G is a group and to prove the subgroup, you had A, B inverse in H. But if it were finite, then you just needed to show closure. You'll see the difference, right? You can't do that for an infinite group, right? How you can show closure in an infinite group, right? Well, sorry, you could. But it is special for... No, because by definition, a group is closed, right? But the theorem wouldn't work because it's a finite group. You know why, right? Because you can't draw... How you could draw an infinite multiplication table? It'll never end. What's up? Right, but if you never stop, the proof never finishes, so you never show anything. So you're wrong. You walk in the exam, you never finish. You didn't even get the hand on the paper. Just no, hold on. Wait, I have one more column. And then the next one. Everybody's okay, right? Because you can't do it. So proof. Okay, so then each left coset of H in G is has the same number of elements as H. You just want to pay attention to how it's phrased, right? Each left coset of H in G. So H is in G, yes? Not G in H, right? So the subset is in the group, yes? Sorry, the subgroup is in the group. Proof, let H be H1 to HM where all those H's are distinct. So we have no repeats, right? We don't have A, and then B. Let X be an element in G. Then the left coset XH consists of XH for I going 1 to M. So now you multiply X by all those elements, yes? Suppose that J, let me just draw that on the board just to make sure you all understand what's going on. Sorry, not draw, right. So we have XH, remember H is H1, H2, HM, yes? So XH would be when we multiply X on the left of all these H's. So these are my elements. Everybody's okay? Suppose that J and K are integers between 1 and M. So in other words, we have some number between 1 and M. So in other words, you have two elements here for which they are both equal. So X by HJ equals to X by HK. So we have that line there, and then we use that to show that HJ equals to HK. And therefore the proof follows from that. Nice. Lagrange's theorem. You all see what's written there in brackets? I added that. So that was one of the additions to the notes. Open brackets. Very, very, very important. Lagrange's theorem. So if you do any sort of abstract algebra, you must come across this theorem. It is like learning to add, more or less. If H is a subgroup of a finite group G, so we have H as a subgroup of a finite group G. So G is a group that is finite, which means that there are elements that end. Then the order. Question, is H finite or not? Obviously it will be finite, right? Because if G finite and H is a subgroup of G, then it has to be finite, yes? Then the order of H is a divisor, meaning that it divides the order of G. So what this is saying, if I have y'all remember what order is? The order of G is the number of elements, right? So the number of elements in a group if you have a subgroup, then the number of elements in that subgroup must divide the number of elements in G. So for example, if the order of G is, somebody call a number. Oh, you could call a prime number. Oh God, man, it's so wicked, eh? So wicked. The order of G is 8. And if I said, hey, well, you know, I have a subgroup, right? So this is like multiple choice questions here. If I were to create, I'll say, let G be a group with order H, order 8. Which of the following are possible subgroups of G? So I have A, H1, such that the order is 1. H2, such that the order, so this will be, so I'm just defining these things. The order will be 2. H3, such that the order is 3. H4, such that the order is 5. I thought I was going with 4. And then what I would do, because I'm, you know, I'm wicked, I'll put A would be H1, and so I'll just mix them up, right? H1 and H3. And I'll put B would just be H1. I'll put C to be H3 and H5, H4. And I'll put D as H1, H2, and H4, and I'll put an E just to make sure you all understand. H1, H2, yeah, H1 and H2. I have now. Good. So could this be the order of H? Will this H be a valid subgroup? Yes or no? Yeah, it will always be. This would be. What will be the element? Oh my God, this is even more beautiful. Part B will be define H, or what is H, or write H. So H would be the identity element. You all see how things happen? Magic comes alive, you know. Is this possible? Yes, because 8 divided by 2 is 4, right? So it divides. Is H3 possible? No, because 3 doesn't divide 8, right? You get a remainder. Is 5 possible? No, it's not possible, right? So our answers are 1, 2, and that's it. So this would be H1 and H2, which is, oh my God, look at this. E. Oh. What's that? This is H4. Catch you. Because I caught myself as well. Y'all okay? So, going back to the very special group. What is my very special group? Y'all remember? G, which is, yes, 1, 1, I minus I. The subgroup was what? And the order of that is 2, and the order of G is 4, and 2 divides 4. You all see it in action? Yes. Which means that if I am given a group, we're using this now, and I'm working out, let's just say S3. Let's just go back. So I have S3 has how many elements? 3 factorial, which is 6, yes? And I have H3, which is a group, yes? Which is a subgroup, yes? Of S3. You all follow? Which means the possible number of elements that A3 could have are 1, 2, and 3. So after you don't have A3, and you know E is there, so it's just 2 more elements. And they figure out the 2 elements, 1, 3, 2, and they figure out 1, 2, 3. Don't bother think again. You all follow? Because it can't have any more. So if you understand this, then it drastically reduces your working. Oh, wait, there's no 4th element or 5th element. You understand how things come together now, right? Making sense. We build in. I knew there was a reason why I had to do that at the start. Yes! Proof. The right cosets of H in G. That's what? Form or forms? Forms, and? Yes, but it's the. So if you have. No, but D is the collective.
No, cosets is what you're using. Cosets is plural.
If you have to use because it would say circles are in the classroom. Yeah. So you're going to cosets.
So it's four.
We did the cosets too.
That's why I asked, you know. That's why I asked. So this is correct here, right? Of course, because I type up the notes. I mean, I know it's correct. The right cosets of H in G, again, you all please remember the word and pay attention, forms a partition of G. You all understand why, right? You all understand why? Because we now spend the last hour explaining that the cosets are an equivalence relation, and equivalence relation partitions the set, yes? So therefore, it forms a partition, which means non-empty disjoint subsets union gives you back the set. Therefore, you could write G as the union of all of those. You have followed? This is the power of partitions. And since they are distinct, if you take the order, the length, the norm, whatever it is you want to call it, because they are distinct, the union sign turns to a plus. You follow? Therefore, so since cosets are just joined, the order of G equals to the order of H by A1 plus the order of H by A2 plus the order of H by AM. And we know that all cosets have the same number of elements, yes? Therefore, all of those would have, say, well, mod H number of elements, yes? The order of H. And there are M elements. So therefore, it's M by mod H. So you add them up. So therefore, we get G equals to M, sorry, the order of G equals to M by the order of H. Which, if you can't see if you're not seeing the order of G over the order of H equals to M, where M is a value, right? Which means that the order of H divides the order of G because you get a value, an integer value. Yes? Good. Definition 3.8. Let H be a subgroup of G if the number of left cosets of H in G is finite, then the number of such cosets is referred to as the index, that should have been bold, of H in G, denoted by square brackets G colon H close square brackets. Everybody's okay? Nice. So going back to our lovely complex example, with our G being 1 minus 1i minus I and H being 1, 1, what would be the order of H in G? The order of H in G for that group and subgroup would be 2. You all follow? Nice. Corollary 3.10. Anybody has any questions? Anybody has any questions? It's good. Let G be a finite group of order n for any element A in G. The order of A is a divisor of n. I don't want to spend too much time on this. Y'all know what the order of an element is? The order of an element n is the number such that G to the n equals to E, yes? So it says that all the elements in a group, the orders of each of those elements must divide the order of G. Y'all okay? And the interesting thing is, if you find an element, let's say the order of G is K, and the order of an element is n, where n is less than K, you could form a cyclic subgroup using that element because you just generated from that element, which is just brilliant. That's cyclic subgroups, which we didn't really touch on the last class that I did on last week Wednesday, right? Again, this is not meant to be an exhaustive coverage of topics. It's just meant to introduce it. Hey, yeah, I know what's going on. Okay, let me see what's going on. For any, so part B in corollary 3.10, for any element in G, A to the n is E. So if G is a group that is finite, any element raised to the order must give you back the identity element. So, if we were to find an example, which example would we choose? Anybody could come up with a great example. My God, sir is brilliant. Yes, it's a cheat, you know. So this is the best example I know. The order of G is 4, which means 1 to the 4 is 1. Minus 1 to the 4, I don't know, I just write it down, it's just 1. I to the 4 is 1. Minus I to the 4 is 1. That is what it says. Let's just see. 1 to the 4 is 1. This is correct. Minus 1 by minus 1 is plus 1 by minus 1 is minus 1 by minus 1 is plus. This gives minus I squared by minus, so this gives I squared by I squared, which is minus 1 by minus 1, which is 1, which is correct. This is the same thing, the minus sign goes off, right? So this gives minus I by minus I by minus I, come on, by minus I. Minus and minus is a plus, minus and minus is a plus, minus I by minus I is minus 1, minus I by minus y is... You all see that? It's brilliant. Brilliant. Theorem 3.11. Every group of prime order is cyclic. Every group of prime order is cyclic. So in other words, if I have a group and the order of the group is a prime number, which means the number of elements in the group is a prime number of elements, then the group is cyclic. You remember what cyclic is, right? So just go back to that. Day 1 notes, review it. I know we didn't spend much time on it, but that's fine. I will not go through the proof of it. It's there. You might need to spend some time understanding it because you have to go back to understand cyclic groups, which we did not cover. Again, that's not the intention. So welcome back. So we're now going to proceed to homomorphisms and isomorphisms. This is generally not the order usually followed, but I'm teaching for learning, and this is bare bones. I mean, calcium and blood and vessels. That is what we're going with. So we are on theorem 4.1, homomorphisms. Definition 4.1. Let G, we'll call that star or asterisk, right? And H, dot be two groups. So a function psi from G to H is a homomorphism from G to H if for all x and y in G, psi of x star y equals to psi x by psi y. That is the definition. Let's read it again. So first we read, now we extract information, we learn, we understand. Yes? Let G and H be groups. So we have two groups, right? We have two groups. A function, so psi is a function. You understand that? Psi is a function, meaning that it is a mapping. It does one thing to a certain number of elements and it gives you something else. Yes? From G, so from one group to a next group. So you're taking elements in G and again, and it maps the elements in H. You all follow what's going on? Nice. And it has to occur for all the elements in G. So in other words, all the elements in G must be used. Yes? Good. Such that psi of open brackets x star y. So this is note 1 x star. So that star there is the operation in G. You all follow? Equals to psi x dot. That dot is the operation in H psi y. You all follow what's going on? Very, very important. Very important. Nice. So, oh, I said I was going to go through this. We'll probably come back to that then. Or just do it tomorrow. Right. So I have psi from G to H. Psi of x. Okay, so let's just say, okay, so let's say alpha. Up to now, I have not defined what psi is, right? I'm just bringing one point here across, right? Psi of x. X comes from where? G. And alpha is in where? You all understand that, right? But alpha is xi. So xi is in H. You all follow? You all okay, right? That is important. You'll understand why coming down. Next. So two things. One, we need to find a phi or define a phi or psi, sorry. Good. Example 4.2. Let n be positive integers. Phi. So now we have phi from z plus, which is our normal group under addition, to the complex numbers minus 0. So that's all the complex numbers minus 0 except 0 with multiply. Defined by such that, so in other words, they give us this. Phi of k is e to the 2 k I pi on n. Yes? They give us this and they ask us to show that phi is a homomorphism. What do we need to show? So we need to show, bare bones definition, we need to take two elements, say k1 and k2. Where k1 and k2 comes from? K1 and k2 comes from my G set, and my G group in this case, Z. And I need to show that phi of k1 plus k2 equals to phi of k1 operation in C, which is multiply by phi of k2. Do you follow? This should just be mathematics. So phi of k1 plus k2 is e to the, wherever you see k, you replace k by k1 plus 2. 2 k1 plus k2 I pi over n. This could be simplified to e to the 2 k1 I pi on n plus 2k2 I pi on n, which equals the, this is plus here, right? So when you add rules and indices, it's multiply, yes? So this is e to the 2k pi I, so it's k1, sorry, over n brackets by e to the 2k2 pi I over n. This here is phi of k2 and this here is phi of k1. You all okay? Full stop. Done. Easy. Homomorphism. full marks, or you have to put for all, right? For all K1, K2 in G, well, in Z. Everybody's okay? Yeah? Any questions? Nice and straightforward, right? Second question. Let R be the set of positive real integers. So don't turn the page, just try it by yourself. You got it all? I will take my time, yes, yes. Right, so let's just start skeleton proof again. So we want to let two elements from here. So X, so let's just take A and B. Our goal is to show what? Our goal is to show that I don't know what is this? Trident, right? We'll use trident. Trident, I'm not thinking what I should have used different Greek symbols, right? So trident of A, our operation is dot in the first group. So A dot B or AB equals the psi of the first, trident. The operation in the second group is plus, yes? Plus B. Yes? Good. That's our goal. We could just probably write it here. So we start. So psi, trident of A dot B is, no, trident of A is trident, is log of AB, right? So this is log of AB. Log of AB is Rules of log, log of A plus log of B. And log of A is trident A, and log of B is trident B. Which implies that psi trident of AB equals to that. And this happens for all AB in R plus. This did not take comma. Everybody's okay? Hence, any questions?
Things like this come from us.
For sure. Definitely. Definitely is going to come. Example 4.4. Anybody has any questions, right? So the hardest thing in a homomorphism question, or one of the hardest things, would be what? To find the homomorphism itself. The question does not give it to you. Yeah? Depending on how the lecture, you might get the homomorphism or you might think. Yeah, you might just have to figure it out. Yeah? Based on the operations from the groups. Example 4.4, let f be a function from g to h defined by f of x equals to EH. EH, what is EH, y'all? The identity in HS for all x in G, where EH is the identity in the group H. Then, for any A and B space there in G, f of AB equals to EH. You all see that, right? And EH is EH by EHS. And EH is f of A. And EH is f of B. Hence, f is a homomorphism. You follow that? F of AB is EH, because that's how we define it. F of anything is EH. EH is an identity, so we could write E by E by E. So we just write EH equals to EH by EH. We take the first EH, and that's F of A. And then we take the second EH, and that's F of B. You all follow? Therefore, we've now shown that F of AB is F of A by F of B. Yeah. The remark is important. This is called the trivial homomorphism or zero homomorphism, which will always hold for any mapping. We don't really care about this, right? This is just trivial, right? This is things you need to know, but we don't really care much. Example 4.6. That is a nice word that's called self-study. Oh my God, that's brilliant. Define a mapping phi from G to H such that G is Z and H is Z2, which is Z on 2Z, which we will do tomorrow. Yeah, so we're not going to go into that, so we'll come back to this. Proposition 4.7, so we want to spend some time on this. Proposition 4.7, properties of homomorphisms. If psi from G to H is a homomorphism of groups, and EH and EG are identities in H and G respectively, then for all X and Y in G, phi of XY equals to phi of X, phi of Y. You all understand, right? Because that's a homomorphism, so it must work. The following hold. So the first two we definitely want to go through. So phi of the identity in G, that is a typo. TYPO. So phi of EG, you all know why? Well, it doesn't make a difference because phi EG, if it's equal to EH, then it's the same thing, right? So So it is not, I knew that, you know. I knew that. Proof. Let's go with proof of part 1. For all A and G, yes? For all A and G. So we take an element in G. That element is the same as when you multiply by the identity, yes? So if we have an element A, we have an element A. A is A by E. A is A by E, yes? But because we are dealing with a homomorphism and we have two identities, we want to be specific, right? So this is the identity in G. You all follow? You all understand why G, right? Because we take elements from G for the homomorphism and carry them to H. Yes? So A is in G. So if we're in G, then the element has to be in G. So the identity is in G. Everybody's okay? Nice. So, which means we have A, E, G equals to A. This is by definition of our identity. And then we take psi on both sides. So, we psi here. And we psi here. And then we use the property of a homomorphism. We know that this is, because it's a homomorphism, psi A, psi of EG. Everybody's okay? Direct properties of homomorphism. And here is where you understand what an identity means. Remember, an identity is any element E such that E by any element is the same element which is A by any element. You all follow? So an element is, this is here is left identity and this is right identity, yes? So once, any time in the whole world ever you see that A by this equals to A, what does that mean? That this is the identity. You all follow? Lovely. So we have this and we have this. Therefore, this is the identity where in H. Remember, A is in the first set and psi of A is in the second set, which is H. So this is an element of H. A is in G and psi of A is in H because it goes from G to H. So therefore this is in H, and similarly here this is in H. So this here, EG is an element in G, so psi of this is an element in H. So this here will be EH. You understand that? So part 1, proposition 4.7. Yeah. We have the second part, which I'd like you all to prove. Just attempt it. Yes, the proof is there, but the proof, or you all know I always have a different proof. So the proof would follow from what we did last week Wednesday in the first session. Let's look at it. I know what you're all thinking, so what is going on? What is part 2? Somebody call part 2 for me. Yes? Nice. Can you all read this aloud for me? Yeah, you all remember last week when we had Ah! You remember what you have to do? What's the first one? This by that equals to, well done. But in this case, you have to understand which E it is, EH or EG. You have to just a little bit more things. And the second part is, well done. Shut up. Once I write it on the board, I need to write it down. Feel like I'm away. You follow? So try it now. You should, I think you might need to. You want a Reddick? Tell me. What we need? We need, in this case, we have psi of x inverse by psi of x. And we need to show that this is equal to the identity where? In H. You all understand? Because psi of anything is an element in H. This is an element in H. Two elements in H must give me an element in H. Yes? Also, what's the next thing? Psi of x inverse equals to EH. You're following the structure, yes? Work it out, work it out. And you want to use this to Everybody's good? And this is psi of x by x inverse y. Why? Anybody? Why? Why we could do this? Because it is a homomorphism, yes? Because it is a homomorphism, it satisfies this property, which is of EG. And we've shown before that psi of EG is EH, yes? Yeah. Similarly here. And again, why do we have to do both sides all the time? I'm listening. Because we do not know if it is commutative or not. Yes? No, abelian is only used for groups. I believe so. You know. I mean, I've never heard somebody say that. It's normally commutative. Is not. You speak about an abelian group, but not really an operation being abelian. You wouldn't say addition is abelian. I don't know. You know, you learn things every day. Right. Anybody has any questions? Part 3 and part 4 are straightforward, right? Take over, try it. You'll take some time, not now, home or something, but please try it. If you all have any difficulties with it, tomorrow we'll do it, right? In fact, yeah, just remind me tomorrow and we'll do it. But please attempt it before. Nice. Note 4.8, since a homomorphism preserves the operation, it preserves the identity and the inverses. Operation, sense. Okay, fair enough. Page 38. Let psi be a homomorphism of G into H. The kernel of psi, denoted by KER psi, is defined by. We are not talking KFC. KER of psi are all the elements in G, which means the first group, such that the image, so in other words, psi of that element, gives the identity in H. You all follow? Remember, psi is a mapping, yes? It's a mapping. We never said it's a one-to-one mapping. If it were a one-to-one mapping, then the identity in G would give me the identity in H. That does not mean that there are other elements in G that cannot be mapped onto elements in H. I mean the identity in H. You all follow what's going on? Everybody's good. Well done. Nice. We will learn up. Theorem 4.10, self-study. Show that, there's no show that there, we need to add that. The kernel, or rather it just says it. Kernel of psi is a normal subgroup of G. We are going to do normal subgroups and quotient groups tomorrow, so we will not attempt this. Yes, this is something for you to come back to. Lemma 4.11. Let psi be from G to H be a homomorphism. Then psi is injective if and only if the kernel of psi is the singleton identity. So if you have a set that only has one element in it, say A, this is called singleton A. This is called singleton P. This is called singleton identity. You follow? Nice. That's new. Is that new to you? That is self-study. So probably tomorrow, maybe, if not at the end. Again, the goal is just cover the absolute basics, the things that I need for you all to understand. 39. On page 39, that continues. That's the proof there. We're not going to go through that proof. Term 4.12, that is for completeness. Don't even bother read that. Right? Definition 4.13. Definition 4.13. Let a function f from G to H be a homomorphism if f is also a one-to-one correspondence, which just means if f is one-to-one, then f is called an isomorphism from G to H. You all follow? That's it. So in other words, you have your homomorphism, which is a function. You prove that your product of A and B equals to the image of the product. So you prove that the image of the product is the product of the images. That gives you the homomorphism. If in addition to that, your function, psi, whatever it is one-to-one, then that homomorphism is called an isomorphism. That's all it says. So now, in addition to doing our working that we did before, we could go back and find out whether those functions that we defined before were one-to-one or not. If they are one-to-one, then we could call all those homomorphisms that we used before isomorphisms. Everybody's okay? Pause. Next one. If f now is a homomorphism and it is one-to-one, meaning that it is an isomorphism, and it is onto, which means that all the elements in H, for all the elements in H there are corresponding elements in G, such that f of G equals to H, an element in H. Then we say that H and H is isomorphic. Sorry, G is isomorphic to H, or H and G are isomorphic. You all understand that? Definitions. So in other words, we have that inverse. The person who actually started the study group, J, that's where I learned this that notation from. I find it's nice. I mean, I can make it mathematical and do the inverse of alpha equals to beta, which means alpha beta equals to E, or beta alpha equals to E, right? Which is the same thing, right? But that just looks nice. You all follow? So it's the same thing. And I remember when he did it, I'm like, oh my god, this is brilliant. So yeah, so this is the mathematical version without all the fluff of the that. Yeah. Where am I? Right, so if we have, you all look at it. If we have a group A, G, we have a next group H, we form a function or a mapping. There's a mapping from G that carries elements to H such that one f of AB is f of A, f of B, meaning that the image f of a product is the product of the images. This is called a homomorphism. Yes? 2, if f is one-to-one, then we call isomorphism. Yes? 3, no, this is and there, each one is and there, so homomorphism and one-to-one is isomorphism. So this last one is and onto. Has to be f, right? F is the only function, right? Can't be G or H. G's are sets and groups. Then we say that G and H are isomorphic, and we write this. Everybody's okay? Which is very, very important in mathematics, because essentially that says you can use elements. There are elements in those sets that act the same as elements in the other set. You all follow? So for example, To answer, we can finally answer, or you can understand the age-old confusion when people say that Z is a subset of R. This is wrong. It is not so. There is a subset of R we can call R star, namely the -3, -2, -1, 0, 1, 2, 3, namely this set, which is a subset of this. This is the exact same thing that acts in identically the same way as the numbers in Z act. Therefore, it is really isomorphic too. You understand that? So the bigger set is, the smaller set is not a subset of the bigger set. It is in the bigger set, there's a proper subset, I shouldn't say proper, there's a subset, and that subset, you create a mapping that is a homomorphism one-to-one and onto with the smaller set, and there's an isomorphism, which means they behave the same. But you can't explain that in standard 5, right? So they just say, well, it's a subset, you know, and it's like, don't tell them that. Y'all okay, right? Nice. We are on isomorphisms A. How to show two groups are isomorphic. If G and H are groups in question, you need to construct. Notice that word construct means you have to think about it. It may not be given. An isomorphism from F to G, so you have to construct an isomorphism F from G to H. So the points are one, so you define a function F that you think might be an isomorphism. Then you prove it's a homomorphism on the board, first point. The second point is you prove it's one-to-one on the board, second point. And the third thing is you show it's onto. Everybody's okay? How to show that two groups are not isomorphic? Well, if it's not isomorphic, any one of the three rules fail. Straightforward. So if two groups are isomorphic, all their structural properties are the same. We'll not go into structural properties. Thus, if one group has some structural property while the other does not, then they are not isomorphic. Example 1, I'll just go into example 1. You all know what Z3 is? Z3 would be 0, 1, and 2, yes? So the remainder 1 divided by 3, yes? And Z4 would be the remainder 1 divided by 4, yes? So 0, 1, 2, 3, yes? Clearly Z3 has 3 elements and Z4 has 4 elements. So you cannot find a mapping that is one-to-one. Because one has 3 elements and one has 4 elements, right? So clearly is not isomorphic. Those groups are not isomorphic. The others I'll leave, 2, 1, 3. Again, my goal here is just to get you all to understand the theory, the specific examples you all could go. But I would like to go to example 4.17 now, because we can actually do this, and I want you all to do this now. So consider the mapping psi from R plus to R plus dot. Show that these groups are isomorphic. So you can try, like now. What's the first thing we need to do? Sure, it's homomorphic, right? Homomorphism. So we take elements in. So let A and B be elements in R. Yes, the first group. You understand the first group, right?
Yeah.
So strictly speaking, if you were to take elements in R plus, you will get 0 because you showed nothing there. You understand? Because psi does not act on elements in R. It's like trying to send a male child to an all-female school. You understand? It's a male child, a boy to an all-female school, or vice versa. You understand? I mean, no, it's just wrong. So now, psi of, and you take two elements, and G is operated. The operation in G is addition. So A plus B, and you want to show that this is psi of what? A, and the operation in B in the second group is multiply. Yes. You just use the definition. So this is, so psi of x is e to the x. So this gives e to the a plus b, which is e to the a multiplied by e to b, which is this. Even the duster is excited. Fine, so hence, and you have to conclude, right? Spell it out explicitly first, right? Hence what? Psi of A plus B equals the psi of A for all A, B in R. Thus, psi is a homomorphism. Everybody's okay? Nice. Now we need to go one-to-one. So because we've taken elements A and B and R already, we don't need to take it again, right? But just to re-emphasize, I mean, I'll just write it back. That's fine with me. Let A and B be elements in R. So assume what? It would be f of A equals to f of B, but our mapping is psi. So it goes psi of A equals to psi of B, and our goal is to show that the elements that we took, which would be A and B, are equal. So this gives psi of A is e to the A equals to e to the B, which implies that A is equal to B. Hence, psi is 1-to-1. Thus, psi is an isomorphism. You all follow? And the last one is to show that it's isomorphic, which means that we need to show it's onto. Did you all attempt this as yet? Yeah, take a minute. For onto, you take an element in your codomain, say y, and you show that there's a corresponding element in your domain, such that f of that corresponding element gives you back y. So if you all remember, when the first thing we did 1-to-1, right? So you all go off to the on. Go back to the contract. It all time. So psi is onto if for all, you understand? Y element of R plus, which is the codomain, there exists and X in R, which is the domain, y'all, such that psi of X equals to Y. Yes?
Yeah.
That's the definition I want to. Take an element in the codomain. If there's an X in R such that always happens and that happens for all Y, then it's onto. So our goal is to find the X. That's our goal, right? So let Y be in R plus if psi of X equals to Y, then psi of X is e to the X equals to Y, which implies that X is ln Y. Yes? Now the question is, will ln Y be in our domain? What is my domain? Real numbers. If Y is 0, ln of 0 is what? Ln of 0 is? Zero. This is e to the x, yes? E to the 0 is 1, yes? This is the line y equals to x, yes? The line y equal to x is the inverse line. E and ln are inverses. More or less. It never touches 0. So this here is ln of x. So just remember the graph. Right, so in other words, this will not, when y is 0, it will not have a value, yes? So technically, the fact that y could be 0 means that there would not be a 0, so this would not be onto, yes? But, because our codomain is R plus, we are sure that y is not 0. You follow? So just let us know that you know that. You follow? Since y is greater than 0, or implies ln y element of R. That's all. Follow? Therefore, psi is onto. Hence, and we conclude big, R plus, R is isomorphic to R plus. Anybody has any questions? So let's do a very, very, very brief review before we end. So the first thing that we were supposed to cover today is cosets, yes? Somebody tell me something. So we have a group G, then from G we have a group H, that is normal, yes? And we introduce the mod H, modulo H, which means that A, B inverse is in H, yes? So we have this is the right or the left coset. This is the right coset, this is the left coset. Yes? Cosets are important because so we show that this relation is an equivalence relation, which means that it partitions the set, and the partitions are themselves the cosets, yes? You all okay? Then we use that fact to say, well, okay, we have G, and if we have G, then we have a subgroup called H. Then we can have, G is a finite group. We can have the distinct cosets H by A1, union H by A2 ... union H by A3. Yes, we could write G, the group, as a union of these cosets, because we know these cosets form a partition of G, yes? Because we've shown that these cosets came from the equivalence relation, and because of this, because these sets are disjoint, then we know A union B, from way in the back, I won't go into that. I was going to say A union B. So the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B, right? But this is 0. Yes? So that's why it's added, yes? Same analysis here, right? But I don't want to bring all of that into this, right? So, which means that if we take the number of elements in G, that is the same as the number of elements in this, plus the number of elements in this, plus the number of elements, let's just call this NM, which means that the number of elements, now because they are all cosets induced by each coset has the same number of elements. So the order of this is the same as this, is the same as this, and there are A to M elements, which means we would have M by the order of each. G, so we get that this here says that the order of each divides the order of G, which is Lagrange's theorem. You follow? You understand the storyline? That is beautiful. After that, we jumped into homomorphism, so we still have a group G to a group H. Now we define a relation, we call it F. I'll use something more sexy. So we call it psi, such that the only thing we were concerned about is that psi of the operation in G, so say A, I'm just going to say plus B, is psi of A times B. The psi of A operation in H, psi of B, yes? This gives homomorphism. If this is one-to-one isomorphism, if this in addition is onto, oh my god, then G is isomorphic to H. Everybody's okay? Nice. Now I'm just going to give you a little step forward. We went through the kernel today, yes? Briefly. There were a few notes on with respect to the kernel that we didn't go into. Just please review them by tonight if possible. Because what we're going to do, tomorrow we're going to use the kernel. Tomorrow we're going to take a group G and then take the kernel of G and form a group. This is a special notation, and that would be isomorphic to a subgroup H. You understand the levels? So we have a group G, then we have all the, so we have a group G. This is the prelim, right? So you have, so this is where the abstraction comes. We will have, just to get you all kind of thinking along the lines, because the more I could think about it and try to understand, I wouldn't really say conceptualize. Because it's abstract algebra, right? You understand? It has to come from somewhere. So you have a group G, then you have a subgroup H. Yes? Then you form a function called phi. Then you have the kernel of the function, which is all the elements in G that map onto the element, the identity in H. Then you form something else called a quotient group, which we'll do tomorrow when we do normal subgroups. So you have G, you form a quotient group with the kernel of the homomorphism. Then you have, and then you show that this here is isomorphic to the normal, to the subgroup H. Yes, you all understand now. So I think that's a good place to end today, right? I hope you all enjoyed the session. It's good. You all learned a lot. Tomorrow, that's the preview for tomorrow. I'd like to thank you all for coming today. I will see you all tomorrow. Enjoy the rest of the day.